Hi, it's my pleasure to have this opportunity to share some our work with you. Um, my name is Gecheng Zha. Actually, a lot of work is done by Yan. He's our CTO. I'm a professor at the University of Miami. So this is from our research, which is mostly originated from aerospace, which I will talk a little bit. So we form a startup trying to commercialize this technology. So the company is called CoFlow Lift. Oh, how do I turn page? Maybe I can. Oh, yeah, I will use this. Okay, okay. So probably for most of you already know, but just as a continuation. So I want to introduce a little background. So 90% of the goods in the world is shipped by marine shipping. So it's a very large provision sector. So annual emission is about 1 gigatons of CO2, and the fuel cost is about 165 billion. That's based on 2019's fuel cost. So something interesting, just for the one of the largest ship, which is not the largest one now, the annual emission is equal to 50 million cars. Obviously, a lot of effort on the electric cars could be just wiped out by one ship. Um, So ocean is actually rich in wind resource. In the old time, we're 100% clean, right, to propel the ships. But you can see that for the ship and the sail, how big it is. Obviously, this conventional soft wind sails is not sufficient for today's heavy duty large cargo ships. But now we kind of like go back to asking for clean energy. So obviously, we'll think about wind resource in the ocean. So I do want to review a little bit about the current technology. So basically, there are three technology here. One is flattened rotor. That's on the left. It is actually originated from very early time by one of the pioneer of aerodynamics, Pronto. Probably anyone studied fluid mechanics know him. What he did is that if a regular cylinder, when the flow passes cylinder, because cylinder is symmetric, it will not generate lift. But once you spin the cylinder, we are actually introducing circulation by the friction of the surface, energize the bounding layer. And once you have circulation, it generates lift. It really depends on how much circulation you put there. This lift coefficient could be quite high. But then when we're talking about such a massive structure, this could be very tall and very big. Spinning such a large structure is not cheap. There could be instability issue. If a little bit not so round, could be unstable. And there's also the other very important factor is called gyroscope effect. Just think about once you're high speed spinning, it's going to stay. But when the ship is tilting to the side based on wave or things, this cylinder will not rotate with the ship. And therefore, it could create a lot of stress on the foundation. So in other words, you need to have very strong foundation and overall weight and construction cost. And also spinning such a high structure is energy-wise could be quite costly. So then the second technology is called the suction wing or called turbo cells. It's actually originated from by Coaster's foundation. This advantage of this one is that it does not spin. It's using brass walls with many small holes. It sucks in the air near the trailing edge, and then it dumps the air away. So from the fluid mechanics point of view, we understand when the air going through many small holes, actually it will suffer quite a large energy loss. So This one does have advantage of without spinning, but energy cost is pretty high. And also the lift coefficient will be a little lower than the flatter rotor. Aerodynamically, there's a very simple and beautiful formulation based on conventional classical potential flow is that CL max, I should write it, but if you're interested, you can write it down. CL max equal to 2 pi multiply parenthesis 1 plus T over C. T is the thickness of the airfoil, maximum thickness of the airfoil, C is the core. So from aerodynamic point of view, cylinder and airfoil is the same. Actually, I don't know if you remember, if you study fluid mechanics and the potential flow lift coefficient formulation begin with the cylinder. That's how the mapping transformation could be done in the old time. They don't have CFD at that time. They have to rely on these analytical solutions. So 2 pi multiplied by T, 1 plus T over C. So cylinder T over C is equal to 1. Typical airfoil, subsonic airfoil would be about 15%. That's T over C. So you can think about cylinder is actually a very good lift generation device. It is particularly good for marine shipping because for marine shipping, the drag is very often not against the traveling direction. It could be on the side, depending on your apparent wing. So let's say if the drag is, if your wing is coming from the side, and then the drag will not do work at all. So in that case, we can make full benefit of the lift coefficient. So the third technology is just simply using aircraft wing. What we know, right? Aircraft wing is a horizontal lift aircraft weight. But for marine shipping, they simply put vertical and generate thrust. Based on the formulation I just mentioned, obviously aircraft wing, you cannot be too thick because they don't use any active flow control. They're simply just using an aircraft wing. So advantage is very simple. Does not need to spin, does not need cost energy, but the lift coefficient is much lower than the other two. So that is the current technology. So our solutions, we love cylinder, but is there a way that we generate lift without rotating the cylinder? That is what we are from. So for this configuration, you can think about when the wing is from the left, for example, on the leeward side, we suck in the wing, a small amount of wing at about the 4 o'clock position. We pressurize and eject it back tangentially at the 12 o'clock position. So this actually generates very high lift coefficient because we can make the flow attach without rotating. It's similar to spinning cylinder, but in a more efficient way and also simpler way. So the technologies originated from aviation. We are still working on that. Actually, I will have lots of slides showing. We are currently working with NASA to fly on Mars using CoFlow jet technology. Why we need this on Mars? Mars air is very thin. It's 100th of the Earth density. If you don't have high lift coefficient, you will not be able to fly there. So you can see this is the airfoil we begin with. For airfoil, we have a pump embedded suction air near trailing edge, pressurize and eject near leading edge. This mechanism of suction and blowing is actually very important because both suction and blowing here energize the boundary layer. It's zero net mass flux flow control. In other words, whatever we suck in equal to whatever we eject out. We only exchange energy in the control volume standpoint of view, but we don't exchange mass flow amount. And also there's a very important mechanism is that we all understand, well, I guess probably most of you all studied the fluid mechanics. For the pressure distribution, the lowest pressure distribution is behind the leading edge. We call it suction peak. So we eject the air when the outside pressure is very low. So obviously, it's very easy to eject, right? And then the pressure where it goes up is called adverse pressure gradient toward trailing edge. The pressure is high, it's very easy to suck in, flow in. So this creates a very low energy expenditure mechanism, which is crucial because obviously, ultimately, the net gain is your lift, drag, and power consumption. Drag and the power consumption should be as low as possible. And this is a testing funded by DARPA. You can see that it's airfoil. As I mentioned, cylinder and airfoil is the same thing. This is not for cylinder, but for airfoil, you can see that the baseline maximum lift coefficient is about 1.4, and we get about 9. So we are talking about almost like 5 times higher. And then the baseline has positive drag. We got very large negative drag. What does that mean? Negative drag means thrust. So, well, here's not the perpetual engine because we put energy by through all these fans. But it does shows a very dramatic drag polar change, means lift versus drag. So here's the video shown in the experiment by PID. So it is, yeah. This is a micro compressor we designed for airfoil. For airfoil, you have to make the fan very small. But for ship, the advantage is that everything's big. It's much easier to make and higher efficiency. So now the flow is stored. This shining surface is the airfoil surface. So once we put the jet on the blue line, you can see flow immediately attached. Lift goes up, drag goes down. And then, this is the photo. This is the velocity field. All is from experiment. When we reach the red line, we'll turn the jet off. You will see the flow go back to stored. See, it is stored again. So now we compare CoFlow jet cylinder with a flattened rotor. So on the left, we're using CoFlow jet. You see that we suck in here and pressure eject here. This point from cylinder, we probably studied that. We understand. Here is the pressure is the highest. Therefore, speed is the highest. Therefore, pressure is the lowest. Therefore, it's good to eject here. And the pressure will continue to go up after this lowest pressure point. When it's high pressure, we suck in. So overall, it's very good energy expenditure, very low. So compared to flattened rotor, we can generate a lot of high lift coefficient. Of course, here, compared to lift coefficient, here's 5. The power coefficient is 0.7. We have 3.3. If the wing is from left, like this one, the net power would be the lift minus power coefficient here. So you can think about here minus this one, we get 12, about 12, right? Here you minus, you get a little bit more than 4. So we're talking about much higher net power coefficient. So we compare with the flattened rotor. We think flattened rotor is actually, from aerodynamic point of view, it is the best technology in the conventional wing cells compared to suction wing and the aircraft wing. We put the disadvantage aside. Now we're just trying to compare aerodynamic performance. So for CoFlow jet, we can go up to 15 of the CL. But you pay a price too. When you see this 15, you can see your power coefficient here is 3.3. If we drop the CL by 50%, let's say to 7.6, the power coefficient dropped almost 10 times. So in other words, the relationship between CL and the PC is exponential. Actually, this relationship also applies to flat rotor. In other words, you don't necessarily always want to use very high lift coefficient because your power coefficient is also high. So what we do now is that when the wing is from the side, we use this high power or high performance, we call it, means high lift, high power. Net power is much larger. When it's head wing, we use low lift and low power. When we say low lift, it's still very high. For example, 7.6 is very high. This is based on 3D simulation. Here is again is the CFD simulation. You can see this cylinder is not spinning, but streamlines all spin around this because the circulation is induced by CoFlow jet. And this is just showing the contours shaping at a different span. So the net power is equal to CL multiplied by sine apparent wing angle minus CD cosine apparent wing angle multiplied by TC, that's the power coefficient, and then multiply the velocity ratio. You have a ship moving velocity, you have apparent wing velocity. So V ratio is equal to ship moving speed divided by apparent wing, and then multiply 0.5 rho V apparent wing cube. That is the net power. In other words, lift, drag, and PC all matters. We cannot just simplify, emphasize the lift. But for example, at the apparent wing, let's say 90 degrees, then this term is zero. Your drag does not do work. But when it's headwind, this cosine, for example, headwind, let's say we can go as low as 15-degree headwind, still generate power. But in that case, your cosine, 75 degrees, is a pretty big number. So all these things matters. Then we compare with a flattened rotor across the wing angle. So we can generate quite positive power at the low speed, but at the headwind and also tailwind. But when the side wing, we like to use high power. So we can basically combine different mode. Let's say when it's side wing like this one at about 100 degrees, for example, we use high lift, high power mode. But with headwind or tailwind, we use the blue one is low lift and low power. But again, when we say low lift, it's just relative to CoFlow jet technology itself, which is actually could be a lot higher than the flattened rotor. So we compare with a different angle. This is just on the numbers, which is showing same thing as the curve. What I want to show here is that we generate positive power. For this case, at the low speed, actually we get positive power. This one is 20 degree. Our current result is 15 degree. I didn't update this one. So, but flattened rotor has to go to 40 degree headwind to generate positive power. And obviously, when we have the side wind, we generate much more power than the flattened rotor. This velocity ratio is 1.3. Previous one is 0.3. So it means this one ship is moving much faster. The faster the ship you move, the more benefit this technology will bring you. Certainly, when you move fast, because your ship power need to be a lot higher too. So percentage-wise, we get more using CoFlow jet. Again, this is compared with the flattened rotor. So this is just one cell with a 3 meter diameter, 24 meter height. We can generate, over 700 kilowatts at 10 meters per second of the apparent wing. Again, this is just a table. So the other thing is that obviously, what we prefer the apparent wing relation with injection is 90-degree relationship. Means when the wings from the side, injection would be at the 12 cross position. So if a wing is this way, we like to adjust the cylinder, also maintain this 90 degree. So obviously, we will have autonomous control or automatically adjust this one. But do we really need to adjust constantly when the wing angle change a little bit? We have adjust a little bit. Not necessary. So we want to see how much angle variation the cylinder can tolerate. So we did an angle of attack study. So here is the low lift mode. If we chop from here, so here's the peak lift. If we chop from here, the range is almost 80 degree from like negative like 30 degree to positive 50 degree. You don't really, yeah, you don't drop a little bit, but not much. And then when it's high lift, it's about 40 degree. So in other words, there's a very large range it can tolerate. That is exactly what we have seen in the airfoil when they go high angle of attack. Basically, airfoil was stored, but the CoFlow jet will remain attached. So this is basically the same thing. So overall, we are hoping to reduce the fuel consumption by 20 to 50% for large cargo ships. For small cargo ships, we are hoping could reduce 60 to 95%. So in other words, for middle to small size cargo ships, there's a hope that wind power could be the dominant word. Obviously, any numbers here make it's very significant. Probably, I don't know if you know that. I just happened to see that the fuel cost for a cargo ship from Shanghai to Los Angeles, round trip 28 days, one trip is about $7 million. And then think about a year, 12 months, you're talking about $70 million or a little more. So if we can save 20%, we are talking about save $14 million just for one shift. So, and this could be also good electrified propulsion for ships. So here's our team. And this is an aircraft we are flying with NASA on Mars now. Well, not flying yet, we are studying. NASA funded us to fly on Mars. So that is basically my presentation. This is using CoFlow technology, exact same technology. I'm open for questions. Yes, please.
Very interesting presentation. Thank you. My question is, you mentioned that the suction sail, the suction wing, is plagued by high power requirements. But don't you have the same problem here? I'm just standing here for very tiny ducts.
Sorry, say it again. The last question.
Yeah. You mentioned the about the suction sail.
Yeah.
The suction wing. That particular idea is plagued by lots of friction. The air has to get through those tiny slits, right?
Yeah.
But how do you avoid that noise? I feel like you would have the same problem.
No, first of all, we use slot. Slot, this is actually a long span. It is bigger than many small holes. So this will reduce the loss. And we have ducts here to guide the flow. In fluid mechanics, we understand there's so-called sudden expansion loss. When any jet, let's say you go through from a small area and suddenly expand the area, there's a very high entropy increase. So that's one way we avoid that. The other thing is that, think about this suction wing. Where they dump the air, mass has to be conserved. When you suck, you must have somewhere throw out the air. And for example, this original Costa's design, they throw it this way. I know now the bottom for blues throw it this way vertically. The way they throw the air has nothing to do with the flow. They have no interaction with the flow. So that is a waste of energy. For CoFlow jet, we dump the air here. So both blowing and suction energize the boundary layer. So we understand boundary layer flow control. You can do injection only or suction, but we combine both together. So other technology does not do this. In the two-dimensional control volume point of view, if we draw control volume this way, flow coming from the left going out to the right. For CoFlow jet, the mass is conserved. Whatever flow going out will be equal to the flow going, whatever flow going in equal to the flow going out. But for this one, if we do a cross section of this one, that's where they control the flow. There's only suction that we don't know where the flow goes. So in a two-dimensional, stream-wise control volume point of view, the flow is not conserved. This actually is very important. It's a necessary condition to be efficient. even though it's not sufficient. In other words, if you want to be sufficient, you must have zero net mass flux flow control, but suction wind does not have. So actually, in this way, you can think about it's suction air, and then you can think of the vertical way air going out would be in the direction perpendicular to this streamwise surface. And the streamwise surface is the most important surface. That's how we control the boundary layer. Yes.
So I mean, generally speaking, for wind assisted propulsion technologies, the level of efficiency increase you get is highly dependent on operating speed. So in the claim of 60 to 95% goal power reduction for small vessels, do you have a design speed condition that you're getting that number from?
We generally prefer the higher the speed, the more beneficial. So we can think this could be used for, in general, any speed.
But that number that you get, though, you know the design operating condition of the vessels that number was calculated for?
Yes, but of course we have to have wind in the ocean. If there's no wind, we cannot use it. But as long as there's a wind, any shipping moving speed could benefit from this technology. Yes.
Can you tell us what the time interval is used for determining the power to spin a rotor? Because if you're going to be on the same tack for a long period of time, then you don't have to accelerate the rotor very quickly. And if you can tolerate a slow acceleration, then the power to spin it goes down remarkably.
You mean, well, we don't need to spin. Do you mean the fan?
But the rotor has to be spun.
Fan and rotor need to spin. We don't need to spin.
Yeah, you said it used a lot of power, but our analysis is that if you don't have to accelerate it very quickly, it doesn't really need a lot of power. It needs a lot of power if you accelerate it quickly. But if you're on the same course for days, you don't care if you accelerate it. No, then you don't need as much power to spin it.
Yeah, I think when we say a lot or not a lot, it probably in the relative sense. You probably feel it is not a lot, but from overall efficiency point of view, it is already a lot. For example, I put here as the here is the flange rotor. At the lift 5, the power coefficient 0.7. That is a lot, but you may think it's not a lot. It really is relative. But if you really want to have high net power, we need to reduce this one. Think about this one. When we have lift coefficient 7.6, our power coefficient is only half of that. So compared to this, we say it is a lot. But if we just compare to flange rotor itself, it's hard to compare, right? That's our mindset is in the old way. We think that's still okay. But we are hoping overall power will be much more substantially reduced.
It's a question from the online audience. Can you please share your approach for changing tack? How are you going from port side to starboard side wind angles?
Say it again, the question.
Can you share your approach for changing tack? In other words, or if the wind angle is coming from the port side, how do you change that for a wind?
When the wind angle change, we rotated the cylinder. Yeah, just based on the wind direction, we can automatically adjust the cylinder. But it is only for adjustment. It's not spinning. And then, as I said, we can tolerate very high angle range. We don't need to always rotate. Maybe, for example, every 20 degrees, the wind change, we just adjust. We don't need to say every degree we change it.
How does the lift coefficient varies throughout the span of the height?
How the lift coefficient?
Yeah.
We just integral along each intersection, get the overall cylinder.
Is it too much different than a Flettner rotor to this?
No, for lift coefficient calculation is the same. Definition is also the same. Yeah, along the span.
Is it the same on the bottom, on the middle, on the top?
No, actually, usually when you are getting closer to the tip, you can see this tip vortex, and it will decrease the lift. So it's not uniform, but more in the bottom or middle is a higher lift coefficient. If you talk about 2D point of view.
So the decrease in this method, is it too much compared to Flettner rotor, or is it?
Oh, you mean the tip effect? I think these two probably similar. It's a three-dimensional effect. You will always have tip vortex effect. That is just like aircraft wing, they put a winglet. Here we put a cap.
Okay, great, thank you very much.
Thank you.